In this video, we look at UML diagrams. UML stands for Unified Modeling Language, and it is nothing but a way of documenting object-oriented systems. So this was developed in the late 90s or early 2000s. It is still evolving by a consortium of organizations in the industry, and it is the standard used in the object-oriented world. So there are three types of diagrams: structure diagrams, behavior diagrams, and interaction diagrams. So structure diagrams show what the system looks like, things like what are the classes, what are the packages. They are independent of time. Then we have behavior diagrams show the behavior of the system or the business process. And then we also show how the various entities interact with each other. We have interaction diagrams. UML is extremely complicated. There are far too many things to cover. We are only going to cover a very small subset of this language. So structure diagrams, we are going to cover class diagrams, object diagrams, and package diagrams. What are they? The class diagram shows what a class looks like. What are the fields, what are the methods, what are the relationships between classes, and so on. Object diagram shows the status of the system at a given point in time. It is used mainly as an example, because a class diagram is a little more, I would say, abstract, whereas an object diagram is showing you a specific situation that might throw a little more light into what things in the class diagram mean. A package diagram shows the various packages of the system, what classes belong to which packages, and so on. We are not going to worry about the other three. Then there are behavior diagrams, how the system behaves in the as a business process. So there are two behavior diagrams that we will be focusing on this semester. One is the use case diagram, and the other one is the state machine diagram. So we'll have one case study which focuses on the use case diagram, how to capture requirements using this model, and the other one using the state machine diagram, or using what are called finite state machines to capture the behavior of a system. We will see what is applicable in a given situation. We will talk about all that when we do the class projects. Then we have interaction diagrams, and we will be mostly focused on what is called a sequence diagram in this course. So this is an example of a class diagram. A class diagram consists of a big box or a small box that is divided into three smaller boxes. In the top box, we write the name of the class, or this could also be an interface, by the way. And then in the second sub box, a small box, we have the names of all the fields and their types. And we put minus in front of a field if it is private, plus if it is public, and pound if it is protected. We put a colon after the field name, and the type is not, I mean, this could be things like integer or double, string, etc. So the format is not as in Java. You don't write string name. You instead of write name, colon, string. Then in the third box, we put all the constructors and methods. Student is a constructor. It has these parameters. Notice the way the parameters are written. We put the parameter name, put a colon, and then put the type, then put a comma, etc., etc. And we are supposed to put all the methods here, but you will find that this is going to be a really difficult task when you have more than a few methods. So one has to find a way to accommodate the methods. Maybe one can choose to ignore all the getters and setters and write only the most important methods. I'm not saying getters and setters are unimportant, but only the less obvious ones here. One has to find some kind of a compromise for those things. Here is an example of what is called a use case. A use case can involve two or more parties. So for example, here we have an interaction between the system and one user. So we have a two-column use case because there are only two parties involved in this particular scenario. So this talks about what happens when a person tries to get some money using a debit card. So what are the actions of the person who is using the system, and what does the system do? So we are not talking about the individual components of the system. We are simply trying to write here the expected behavior. This is writing out the requirements. How it is not about how the system carries out the task. You should never write how the system will actually carry out the task. That is what is the underlying data structures. We do not write those kinds of things. So here we write things like insert debit card in the insert card slot. Then the system should ask for the PIN number. The user should then enter the PIN number. It should verify the system should verify the PIN, and if the PIN is invalid, it displays an error, and then go to step 8. So you can see there is a go to statement here. Otherwise, this is more like an else statement. As for the amount, the actor enters the amount, then the user enters you can read all this. So this is a complete interaction between a user of the system and the system. It starts from a particular situation where here the situation could be that the person wants some money. So that could actually be step 0. You could say, or step 1, it doesn't really matter much. You could write that a person wants to borrow some, or not borrow, take out some money from the account. And you write the step numbers 1, 2, 3, 4, etc. You write everything in complete sentences or almost complete sentences. One could say this is not a complete sentence. Or this is not a complete sentence because we don't have the nouns here. The noun is supposed to be the actor here in this column and the system in this column. You should write things grammatically correct. It should be in the active voice, and you should not cut corners. For example, if the system asks for the PIN number, you should write that here and then say the user enters the PIN number. You should not say the system reads in the PIN number and then verifies it all in one step. No, you should not do those kinds of things. Then we have sequence diagrams. Sequence diagrams would be our main tool for depicting the interaction of the various components of the system. So we are now breaking down the system into individual parts. Like we are saying the system here, where the user takes out some money, is actually formed by an ATM machine, a bank account, and a collection of accounts. Whether this design is correct or not is not the issue per se for this particular slide. Of course, it is important for an actual application, but that is not the main focus here. The purpose of this slide is to show you what a sequence diagram looks like. It shows the internal design of a part of the system. So the part of the system that deals with money, mm, taking money out of the account is, that design is shown here. So this is the requirement, the use case, and this is the corresponding realization, the corresponding design of that particular requirement. So here we have the customer inserts the ATM card. So some of these steps really correspond to steps in the use case, and the system asks for the PIN. So here the system asks for the PIN, but here we are saying it is the ATM machine that asks for the PIN. The user enters the PIN, which is from here, and the verification is done like this. The ATM machine sends a message to the accounts object. So these are all objects. ATM machine is an object, bank account is an object, account is an object. So we have space here. This is the horizontal thing is space. These are in different places, and time is increasing as we go from top to bottom. And we have to show the interaction between the or among the different objects. So the ATM machine sends a message to the account saying get account, and then passes the card number. Then the accounts does some work within that object to retrieve the account corresponding to the card number, and we return an account. We cannot show all the details. Maybe this card number is invalid, in which case the account would be null. But we simply say it returns an account, and if it is important that the account not be null. So in the next sentence, we are saying we are verifying the PIN only if the account is not null. So this is called a guard. So we are sending a message to the bank account saying, verify that the PIN is correct, and the bank account verifies that. Then it returns a value, verified or not. We are, again, not writing out everything. So we are assuming that this is going to be a Boolean from the way the message is written. It is said verified or not. So we are assuming it is a Boolean. We can't show all the details. If you show all the details here, it would be like pseudocode, or it would be even like Java code. We don't want to do all that. So only the broad steps are shown, but we have to show sufficient detail. So we have to be able to gather the functionalities of these different objects from the sequence diagrams. For example, the accounts object has to have a method called get account, or the bank account object class should have a verify PIN method that returns a Boolean, and so on and so forth. So remember the big things. This is showing the design. A sequence diagram shows the design corresponding to a specific use case. So there is a one-to-one correspondence between a use case and a sequence diagram. A use case says what the requirements are, and the sequence diagram shows how those requirements are met, what the design is, which objects are participating in carrying out the task, the various interactions among the entities, the actors, the ATM machine, the bank account, the accounts, etc. in this particular case are shown as messages and return values. Then we use the class diagram, the notion of that, for depicting interfaces. So for example, here is a student list interface. So if you have a Java interface, we show its design like this, but notice that the interface is actually italicized. This means it is abstract, and we put the word interface in angle brackets here, double angle brackets. We put all the methods over here. Usually there are no fields, right? You can have static fields, though, static final fields in interfaces, but probably there is little reason to show them. And if a class like student linked list implements student list, we show it like this with dotted arrows. Class relationships are shown like this. Student registers for courses, or maybe this should be sections. It doesn't really matter much. It is a many-to-many relationship. We used to put stars on both sides of the relationship. We write the name of the relationship